Okay. So the Hartree-Fock determinant is invariant to rotation of orbitals, but let's see if the IEPA is invariant to the rotation of orbitals. Now the correlation energy, or particularly the pair correlation energy as it is called in IEPA, the calculation involves certain integrals. So you have all the integrals of the type A, B, R, S, so all kinds of integrals, which we have to evaluate. So what was the expression, once again, of the pair correlation energy? So for every pair AB of occupied orbitals, you have a sum of over all the unique virtual orbitals, and you have the matrix element of the Hamiltonian between the ground state function, the Hartree-Fock determinant, and the correlating determinants, which are the excited determinants, as they are called in the numerator. And in the denominator, you have the matrix elements of the Hamiltonian minus the Hartree-Fock energy between the same excited determinants minus the pair correlation energy. So this is an equation. So this term is basically the correlation energy introduced by the psi AB to RS determinant. Anyway, so some of the integrals which are involved in calculating this pair correlation energy, and also the pair correlation function psi AB which involves the coefficients CAB to TU and the sum over all the unique TU pairs is again the pair correlation energy. Okay, so these are the two equations that need to be solved in order to obtain the IPA function, and the integrals involved there are integrals which look like AAAA, AB, RS, etc. So let's see what the values of these integrals are. So for example, let's take the simplest one, which is AAAA. That is equal to an integration of 1 by root 2, 1, 1 plus 1, 2. So here we are always assuming real orbitals. And this is the spatial integral. So I've integrated out the spin coordinates already. Square dr1 dr2 that is equal to 1/4 integration one squared 1 by r1 2 1 squared dr1 dr2 plus 1/4 1 2 squared 1 by r1 2 1 2 squared dr1 dr2. So and because 1 1 and 1 2 are very far apart. So these are the localized orbitals. The cross terms are 0. So now you have, and also 1, 1 and 1, 2 are basically the same orbital. I mean, the values of the integrals will turn out to be the same. And I can denote that as 1, 1, 1, 1. And I have 2 of them. So 2 by 4. So that is half. And you can call this the Coulomb integral of orbital 1. So J11. Okay. Then you also have, let's say, some R type orbitals. This is, so all the R orbitals involve the unoccupied orbitals of type 2. So analogously, this is half of J 2, 2. And this is also the same as S, because R and S are also, they look like the same functions. And this is also equal to RRSS. Also equal to RS, because they're all basically the same. Okay. Then you have RRAA, which is the occupied, unoccupied. So they are different functions. So it is a different Coulomb integral, which we can call J12. And these 1, 2 and 2, 2, they refer to the electron number, because this is the spatial orbital and Mulliken rotation, remember. So the bra part is electron, belongs to electron 1, and the ket part belongs to electron 2. So this is a Coulomb repulsion between orbital R and A. R contains electron 1 and A contains electron 2, so it is J12. And these are also equal to another set of integrals. We have RA. That is important. This is again a different interaction, because this is again 1, 1, 2, 2. So this is an exchange interaction of electron 1 and 2. So that is called K12. Okay. Now at the orbital energy level, what do we know? We know that the occupied orbital energies are the same, which we call E1, and the unoccupied orbital energies are also the same, which we call E2. Okay. Now our goal is to calculate the various paired correlation energies. So what are the pair correlation energies that we have to get here? So we need to find out E A bar, E B bar, which are equal. We have to find that out. We have to find out E E A B bar, E A bar B. So these are also equal, but we need to find them out. And we also need to find out E A B equal to E A bar B bar. So we have 6 pair correlation energies that we need to find out. Out 1 or 2 just to see how it is done, and then I'll just write the expressions for the others. So let's say I want to do EAA bar. The function psi AA bar is equal to ground state. So AA bar is Gerardet symmetry, and it's a closed shell singlet. So I only write determinants which are of the same space spin symmetry. So psi 0 plus C1 psi AA bar RR bar, and C2 psi AA bar SS bar. So this is the function that I want, Gerardet symmetry. Now, to reduce the number of variables that we need to find out, what we can do is instead of taking two separate doubly excited determinants, we can take a linear combination of them as the excited determinant. So from these two excited determinants, we can form a symmetric combination as well as an anti-symmetric combination. Now, since the only one which will mix with my AA bar is of Girardet symmetry, we only need the symmetric combination. So we define a new doubly excited determinant, which is psi AA bar, and which we call star star. So star can be R or S, or R and S, let's say. So 1 by root 2 psi AA bar R bar plus psi AA bar SS bar. So this is what I'm doing this to reduce the number of variables that I want to get, that I need to evaluate. So my function now becomes and the value of this, of the matrix element of the Hamiltonian between this excited function and the ground state, Hartree-Fock determinant, is 1 by root 2 K12. Okay, at this point, let me give you a note of caution. So I keep saying psi 0 is the ground state Hartree-Fock function, and these psi A bar RR bar is the excited determinant. But this is only when in reference to the CI expansion that I am doing. We are actually determining the correlation energy for the ground state of the molecule. So the correlation energy is for the ground state. So this is not an excited state calculation as such. These are excited determinants relative to the Hartree-Fock determinant. So don't get confused by the language. Okay, anyway, so the value of this determinant turns out to be 1 by root 2 K12. Now, how that is the case, let's work it out. So I'll just do one, don't worry, because otherwise we'll keep working out things all day. So RR bar, that is by Slater's rules, that is equal to AA bar, RR bar. And this is, so now I'm integrating the spin, still in Dirac notation. Now the exchange part on spin integration is 0. Now I write it in spatial mullicans, AR, AR, and that is denoted by K12. Simple. And this is the same value for AS as well. Therefore, the starred function, the matrix element of the starred function, is 1 by root 2, half of K12 plus half of K12, which is 1 by root 2 K12. Okay? So it's clear how we evaluate the matrix element. And when you, so this will take care of the numerators that I want. So now we have enough information for the so we have enough information for the numerators. Now the denominator you can do for homework. It's a lot of algebra, but it's simple enough. So you just have to open out the determinants and place all the values of the integrals. So you can do this psi AA bar star star H minus E0 psi A bar star star. is equal to what? Okay. You can do this for homework. And for now, I will just write it as a shorthand notation as 2 delta prime. You will get some expression, which I denote as 2 delta prime, analogous to the 2 delta that you did for with the localized orbital. So with the localized orbital, this sort of denominator integral was denoted as 2 delta. So this is a different value, so I'm writing delta prime. And then when you put these expressions into your expression for pair correlation energy, you get EA bar is equal to delta prime minus delta prime square plus K12 square by 2 whole to the power half. So this I'm just telling you, okay, I'm not deriving it, but again, it involves quite a bit of algebra. If you remember your expression from before with the localized orbitals, so there are 2 differences. One is it's a delta prime involved and not a delta. So those are 2 different expressions, and there is a 2 over here. Otherwise, it looks, the form of the expression is the same. Okay. Now, the next type of pair correlation energy is EAB equal to EA bar B bar. And the value of this is basically 0. Now, let's see why. So, psi A bar B bar, for example, is psi 0 plus C1 psi A bar B bar to R bar S bar. Again, it has to be same space spin symmetry. So these are 2 beta orbitals. So here the excited determinant should also have 2 beta spin orbitals. And then the expectation, the matrix element of the Hamiltonian is A bar, B bar, R bar. And this is equal to A bar, B bar. No, sorry, let me integrate the spin. So A, B, R, S, spatial minus A, B, S, R, spatial. Now write it in Mulliken spatial. So A, R, B, S minus A, S, B, R. The 2 values are equal with real orbitals. So this is 0. Okay. So this basically tells you that electron pairs involving electrons of the same spin don't contribute a correlation energy to the IEPA ground state. So this is because, again, that the same spin correlation is already included in the Hartree-Fock function. So at this first level of inclusion of correlation, the same spin correlations do not enter. So it's a reflection of that fact. Then the other pairs that remain is EAB bar and EA bar B. So what are the values of this? I will just write it down. So here again, we take this sort of start function. So psi AB bar pair function is written as Hartree-Fock determinant plus coefficient into psi AB bar star star. So what is the star star in this case? It is AB bar star star is equal to 1 by root 2 psi AB bar RS bar plus psi AB bar SR bar. Okay. then you get equations which are similar to AA bar. And you get some energy from it. And actually the energy will turn out to be the same because the equations are the same. So this basically turns out to be the same as AA bar. And why is that? Because A and B are basically the same function. So something that looks like AB bar is fundamentally the same as AA bar. And since these are now fully delocalized functions, nothing becomes zero because of distance. So now let's look at the total correlation energy. What's the time? Okay, we have enough time. So the total correlation energy of the dimer at the IEPA level with delocalized orbitals, D for delocalized, is equal to the sum of all the pair correlation energies. So 6 of them. So these are 0. So same spin ones are 0. AA bar, AB bar are definitely the same. So is AB bar and A bar B because A and B are basically the same orbitals. So I have 4 E A bar. Okay. And this is basically 4 times then delta prime minus delta prime square plus k12 by 2 k1 square 2 square by 2 to the power half. Okay. And if you remember the correlation energy with the localized orbitals, that is IEPA localized, that is equal to 2 delta minus delta square plus k12 square to the power half. Oh, sorry, what did I do here? So it was so two differences, delta and delta prime are different, and you have a factor of 2 here and no factor here. So definitely the two correlation energies are very, very different. Now to know exactly how different, we need the expression for delta prime. So I will write it here and you can match it when you work it out. That is epsilon 2. So this is the difference in orbital energies. Then you have the Coulomb repulsion 4J12 plus 2K12. And 2 delta is equal to 2 epsilon 2 minus epsilon 1 plus J11 plus J22 minus 4J12 plus 2K12. So how different are they? So basically the difference lies over here in the Coulomb repulsions and also the exchange. So there is at the orbital energy level they are the same, but in the interactions between the electrons there is a difference both in the Coulomb interaction and the exchange interaction. And if you use some numeric values for integrals in some basis, you'll find Szabo and Oslin gives you some typical values in a basis. The two correlation energies can almost be double of one another. So there can be a factor of 2 difference, which really limits the utility of the independent electron pair approximation theory. So there, potentially the localized orbitals are the ones which are more accurate because they give you the correct physical limit of the problem in the dissociated limit. It's size consistent. But with the delocalized, you can get arbitrary energies. So that makes it less useful. Okay. Now, double CI on the other hand, it is invariant to rotation of orbitals. So you get the same correlation energy whether you use localized orbitals or delocalized orbitals. But both of these calculations are not size consistent. So you already have a dilemma. Which one should you do? One is unreliable, but in a certain limit, you get a physically correct energy, and the other is reliable but wrong. So you see that various electronic structure theories suffer from various problems. So in trying to gain one advantage in describing some physics, you lose something else. So that is why this universal theory of determining electronic structure still does not exist. So the most reliable is the full CI, which is not doable for realistic systems. And all the ones which are doable have one or the other problem. So you have to be aware of the problem, the problems of the theory, the needs of the application that you are tackling, as well as where to look for problems if you encounter a result which is not correct. So it continues to be a challenge to even to use methods, electronic structure methods. And when people just blindly run a theory and report an answer, you should always take it with a pinch of salt. So unless they give you additional information about why they think their result is correct, it has no meaning whatsoever. Okay. So even at the simplest level, you see you already have a problem. So double CI is almost the simplest correlation energy. IEPA is also a simple one, but you still don't know which is better. And you can show that analytically that there are problems with either of them. So it's not like you can write a smart program and solve it. So you should good to be aware of this, even if you turn out to be experimentalists at some point. Most like journals, they ask you to present computations in support of your experiment, because even experiments are not infallible, right? So they also have their error bars and their issues with potential contamination, errors in measurement, whatever. So does theory. So it's only when you have very adequate support of one with the other, you can trust your results. So it's a good thing to know both, actually. So what is, okay, so it's 10:40. So should I start second quantization? Okay, let me just introduce second quantization. So I am stopping the coupled pair theories or independent electron pair theory here. You can read a little more about it in Szabo and Oslund. They also have something called the coupled electron pair theory, which is also leads to the coupled cluster approximation. I will get back to it after I have told you the formalism of second quantization, because then it becomes easier to explain. Okay? But if you like, you can also read it up as a follow-up of IPA. It's no problem. Okay, so with second quantization, the idea is that if you have that you transfer the properties of antisymmetry of determinants to operators. So you don't talk about determinants anymore. You do talk about orbitals and how many electrons they contain, or which ones contain electrons and which ones don't, but you don't have the determinant representation. So if you have been working out the derivations that we've done so far, it involves writing out a lot of integrals and lots of indices, and to be frank, it's a bit clumsy. And with more number of electrons, you will simply not be able to manage to write such big integrals. Okay, and then to keep track of what is happening, which orbital is starred, where the signs come. So that's a bit difficult. So second quantization solves this problem by reducing them to algebraic rules. Okay, and so that's what we would like to introduce, and it's pretty simple. So let me just start over here. So in this basically we go back to the first chapter of Szabo and Ostrand. Okay, so it's section 2.4 in Szabo Ostrand. Sorry, this is then the second chapter, section 2.4 of Szabo Ostrand, where they have a very short and neat introduction to second quantization. For the couple cluster theory, we'll go to a different book, which I will email to you. So the concept of second quantization is that you have some operators which are called creation and annihilation operators. And they create or destroy electrons in orbitals when they act on the wave function containing made up of these orbitals. And the algebraic properties of these operators, they tell you the properties of the wave function. So let's see. So we define an operator, AI dagger, by its action on a determinant. So if you have a determinant which has, let's say, chi k, chi l, blah, 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 to chi n, let's say. So I have a determinant made up of these orbitals, and I say that I create, these are spin orbitals. And I'm saying that I'm creating an electron in orbital I, which basically means that I add a spin orbital chi I to the determinant that I had before. So this was an n electron determinant, and this is now an n plus 1 electron determinant. So I have created an electron in orbital I. And the action, note that the action of the operator is always at the nearest position of the determinant. So it did not create chi I at an arbitrary position or at the end or in the middle. It created it right next to it. Okay. Then if you have now creation operators acting on this old n electron determinant. Then you will generate chi j first and then chi I over here, and the rest remain the same. This is the action of ij. Now if you reversed the order of action, you would get chi j, chi I, chi k, chi l, blah, blah, blah. Now remember that the position of orbitals in a determinant are important, and the two determinants that connect by arrows, they differ in sign okay? So this is basically equal to minus of chi I, chi j, chi k, chi l, chi n. Therefore, I get one operator relation now. So I can add this equation. So equation 1 and equation 1 and equation 2. So 1 plus 2 tells me that AI dagger, AJ dagger plus AJ dagger, AI dagger is equal to 0. And this is called an anti-commutator of AI dagger and AJ dagger. And it is denoted by these curly braces. And this is called an anti-commutator. It's called an anti-commutator because of the plus sign. A commutator would have a negative sign. Okay? So this is one operator relation that we have, which also means that AI dagger, AJ dagger is equal to minus of AJ dagger, AI dagger. So if I have a string of such creation operators, then I can interchange positions of adjacent creation operators by changing the sign of the expression. Okay. Also, so this is about the creation operators. Now, the other thing that is built into the algebra of these operators is the Pauli exclusion principle. So, if I is equal to j. Okay, so something I didn't mention. So why could I directly write the operator relation? So when I add 1 and 2, I still have the action of this combination of operators on the determinant, right? But this determinant is an arbitrary determinant. So that tells me that the operator relation is also true. So this is something you've come across before, right? So if you have the action of an operator on an arbitrary function is equal to 0 or is equal to 0, then you can say that the operator itself is 0. So we're using that fact here as well. Got to mention that. So now if I is equal to j, then I have AI dagger plus AI dagger. AI dagger. this is equal to 0, which means that AI dagger itself is equal to 0. So what does this mean? That you cannot create 2 electrons in spin orbital I. And what do we know this as? We know this as the Pauli exclusion principle. Right. So you cannot create 2 electrons in the same spin orbital. And that is a part of the algebra of the creation operators. Now there's also the annihilation operators. So they are also similarly defined. So, annihilation operators. So what does an annihilation operator do? So it's written without a dagger. So AI destroys an electron in spin orbital I. So if I have chi I, k blah blah, this will give me chi k. So this was an n electron. Determine this is a n minus 1 electron. Here also AI can only act on the orbital that is closest to it. So if, for example, my determinant had chi I somewhere in the middle, okay, or let me do let's not put dots because I need to know how many orbitals I need to interchange. So let's say I just had that, a 3 electron determinant. Then you have to first get chi I near AI. And this is 1 interchange, so you will get a minus sign, and chi k chi n. And this will be then minus of chi k chi n. So this you have to always remember, that creation and annihilation operators can only act on orbitals which are right next to it. Okay. Now, then let's look at the anti-commutation relation now. So if I have AI AJ and AJAI. Now notice that it is difficult to do this in the same way as we did the creation operators, because the sign of the function depends on where chi I was originally placed. So before we do the relation of these two, whether they commute or anti-commute, or if they don't do anything at all, we must look at why AI dagger is called the adjoint of AI. So why AI dagger is the adjoint of AI. So to see this, let's do an example. So I have a determinant which of 2 spin orbitals, chi I, chi j, and this you can then write as AI dagger chi j if you like, right? And if I take an adjoint of k, so from get k I go to bra k, I will get chi j AI dagger, which is equal to chi j AI. Okay. So AI is an adjoint of AI dagger by construction here. Like that is how I've defined it. But whether AI is a destruction operator or not remains to be seen. So to do that, I take the overlap of K with itself, and here I have chi j, then AI K. And so this is 1 is equal to chi j AI K. So if I define chi j as equal to AI K, then I satisfy equation 3. Which means that AI acting on K, which is chi I chi j, gives me chi j. So effectively, AI destroys the electron in chi I. Did you get my argument? Destroys electron in chi I. So if I define an operator as an adjoint of the creation operator, then I can show that it destroys an electron in chi I. So a annihilation operator is the adjoint of a creation operator. Okay, now let's see how to get the relation of two destruction or annihilation operators. So to do that, I take the anti-commutation relation of the creation operators. And now that I know that my destruction operator is the dagger of the creation operator, I simply take a dagger of the whole expression. And remember that AB dagger is equal to B dagger, A dagger. So the order, remember that the order gets reversed. Therefore, when I take AI dagger, AJ dagger, dagger, I get AJ, AI plus AI, AJ is equal to 0, which means that the anti-commute, so this is also the anti-commutator of AI, AJ. So AI, AJ anti-commutator is also 0. So the creation operators anti-commute, the annihilation operators also anti-commute among themselves. Okay? And you cannot create two electrons in the same orbital from the anti-commutation of the destruction operators, you can also conclude that you cannot destroy two electrons in the same orbital, which is also a part of the Pauli exclusion principle. The two electrons simply cannot exist in the same orbital. Okay. So if I equal to J, then AI. Fine. So we'll stop here for today. So we've just started on the creation annihilation operators. I'll recap this on Thursday and continue. And eventually we should be able to start the cluster formalism. Okay. So Someone please stop the recording now. I'm stopping the broadcast.